You sit down, press a key, and somewhere on the other side of the world, a machine is desperately trying not to mess up the tiniest piece of plastic in your entire setup. That's the crazy part about mechanical keyboard switches. They feel so simple under your fingers, but behind every single click is a full-blown industrial process obsessed with fractions of a millimeter and fractions of a gram of force. Think about it. You've probably pressed keys millions of times in your life, but have you ever really pictured what happens before that switch ever lands on your keyboard's PCB? Before it ends up in some unboxing video with thok tests and slow-motion sound captures, that switch lived an entire previous life in a noisy factory filled with molten plastic, high-speed presses, optical sensors, and people in lab coats arguing over spring tolerances. That's the world you're about to step into. Let's start at the very beginning before there's even a recognizable switch to talk about. The story doesn't begin with colors like red, brown, or blue. It begins with steel to make the plastic parts of a switch. Top housing, bottom housing, stem. Manufacturers first need molds. These molds are blocks of hardened tool steel, and they're one of the most expensive, time-consuming parts of the whole process. Engineers spend weeks designing the cavities inside these blocks so that when molten plastic is injected at high pressure, it fills every tiny channel perfectly, cools evenly, and pops out as a precise, consistent part. If the mold is even slightly off, the stem might wobble, the housing might not close tightly, or the pins might not align with the PCB. That's the fun of switch manufacturing. If you're off by just a hair, the whole thing feels cheap. Once those molds are ready, the plastic phase begins. Huge bags of plastic pellets, often variants of polycarbonate or nylon, are fed into injection molding machines. Inside, heaters bring the pellets to a molten state, and a screw mechanism pushes the hot plastic into the mold cavities with intense pressure. In a few seconds, the channel that was once empty is full of liquid plastic. Then it cools. The mold opens. Out comes what looks like a weird tree made of tiny parts connected by thin plastic runners. Each branch on that tree is a switch component waiting to be freed. At this point, nothing looks premium. Workers or automated cutters separate the parts from the runners, remove sprues, and sometimes tumble them or lightly polish them if needed. Tiny bits of leftover plastic can cause scratchy stems or housings that don't fit tightly, so even this apparently boring step is crucial. This is where the first wave of quality control lives. Workers quickly scan for warped stems, broken housings, or color inconsistencies. If a batch is off shade from what a client ordered, say a custom lavender or deep teal designed by a popular keyboard creator, it might get rejected outright. Meanwhile, something far less visible but just as important is being created: metal components. Deep inside every mechanical switch is a simple idea. 2 pieces of metal touch and your key press is registered. But getting that to happen at the right moment with the right feel is an art. Manufacturers start with long metal strips, typically made of copper alloys for conductivity and springiness. These strips go into stamping machines that punch out and form the contact leaves. The machines bend, notch, and shape each leaf so that once it's installed inside the housing, pressing the stem will move the leaf just enough to close the circuit. Then there are the springs, the unsung heroes of your typing experience. These springs are made from steel wire that's coiled with precise tension. Change the wire thickness or the number of coils, and suddenly you've created a 35-gram featherlight switch or a 67-gram heavy hitter. Now, picture this. On one side of the factory, you have trays filled with bottom housings. On another side, bins of stems in different shapes and colors. Somewhere else, boxes of springs, rows of metal leaves, maybe tiny vials of lubricant. All of these are about to be brought together on an assembly line that looks like chaos but operates with ruthless order. In a typical modern setup, bottom housings move down a conveyor or indexing table. The first station inserts the metal leaf in the stationary contact piece. The parts need to sit in precise grooves inside the housing, so machines use guides, pins, and sometimes cameras to make sure everything is aligned. If a leaf sits too high or too low, the actuation point of the switch shifts, and suddenly your linear gaming switch feels mushy or unpredictable. The assembly line lowers a stem onto each spring, guiding the cross-shaped top into position so it doesn't scratch or deform the internal walls of the housing. Then, in another station, the top housing is placed over the entire assembly and snapped into place using the small clips molded into both pieces. With a quick clack of plastic on plastic, the switch's body is sealed. At this point, what you recognize as a mechanical switch finally exists, but the journey is not over. Now comes testing. Some factories use random sampling, pulling switches from a batch and running them through keystroke machines that press each switch tens of thousands of times to ensure it doesn't fail prematurely. Others use more advanced tools, optical sensors or force displacement graphs, to measure the exact curve of the key press. How much force it takes to start moving, how much force at the bump, how sharp the drop is after actuation, and how quickly it returns. If that curve doesn't match the design spec, the batch might be flagged for issues. This is also where factory lubrication comes in for certain lines of switches. Some budget switches skip lube entirely to save cost, but higher-end or enthusiast-focused lines might have small amounts of lubricant pre-applied to the stem rails, the slider surfaces, or the spring ends. This reduces scratchiness, stabilizes the feel, and can even dampen noise. Getting this right at scale is hard. Too much lube and the switch feels sluggish or mushy. Too little and users complain that it feels sandy. Some manufacturers use micro-dispensing machines. Others rely on workers with fine tools and a lot of repetition. But lubrication and precision aren't the only secrets hiding inside a good switch. There's also the choice of plastic itself, and this is where things get surprisingly nerdy. Different switch makers mix and match materials like nylon, polycarbonate, and POM for very specific reasons. Nylon housings tend to give a deeper, fuller sound, making each press feel a bit more thocky and muted. Polycarbonate, on the other hand, is harder and can sound a little brighter, a bit more sharp and snappy, especially when paired with a firm plate and hard keycaps. Then there's POM, often used for stems because it's naturally slick and low friction, which is why so many switches feel smoother than they did a decade ago. Factories don't just pick these plastics at random, they test combinations the same way enthusiasts do, changing just one variable at a time to see how it affects sound and feel. A nylon bottom with a polycarbonate top might give one profile, while full POM housings lean in a completely different direction. Multiply that by different stem designs and spring weights, and suddenly you've got an entire ecosystem of switches born from a handful of base materials. All of this effort is chasing one simple goal: making a switch that feels good for an absurdly long time. Many modern mechanical switches are rated for tens of millions of presses, sometimes even stretching toward the 100 million mark. That durability rating isn't just marketing. It's backed by machines in the factory, pounding these tiny parts over and over until they either fail or refuse to. Zoom out from one switch to an entire batch and you start to see the scale. Thousands of switches are stored in plastic trays or hoppers. Then they're counted, either by weight or by optical counting machines, and bagged into retail quantities, 70, 90, 110, or bulk packs. These bags get labeled with force rating type, linear, tactile, clicky, colorway, and branding. From there, they're packed into boxes, loaded onto pallets, and shipped out to keyboard brands, custom kit makers, or directly to enthusiasts who will film them, test them, and judge them brutally on forums and in reviews. To really appreciate how far this process has come, it helps to glance backward. Mechanical switches evolved from older typing mechanisms, early typewriters, then electric keyboards, then terminals and office machines. In those days, the focus was on durability and reliability more than feel. But as personal computers spread, brands like Cherry, Alps, Topre, and IBM introduced sturdier, more precise switch mechanisms. The classic buckling spring, for example, used a coiled spring that physically snapped as it buckled, creating a loud click and a highly tactile feel. Over time, the industry shifted toward more compact, replaceable switches like the ones we now know, modular devices where each key is its own tiny machine. What's wild today is how much customization has exploded. Manufacturers no longer make just a standard office switch. Now there are infinitely varied lineups: silent linears with built-in dampeners, mid-force tactiles tuned for long typing sessions, ultralight linears for fast gaming, and aggressively loud clickies designed more for fun than for open-plan offices. These all stem from tiny changes in the manufacturing process. A slightly different stem mold, a revised spring, a new plastic blend, or a different factory lubricant. There's also a whole world of collaboration behind the scenes. Enthusiast designers work with factories to create limited runs with unique features: long pole stems that bottom out sooner for a snappier feel, box-style stems with extra stability to cut wobble, or custom-colored housings that match specific keycap sets. On the factory floor, these custom projects might mean swapping molds, changing spring stock, and even reconfiguring lubrication settings just to deliver a slightly different feel that only a niche audience truly understands. And then comes the final transformation, the one you're most familiar with: switches meet keyboards. In hot swap boards, switches are pressed into sockets on the PCB, their pins aligning with metal contacts that let you swap them anytime you want. In soldered boards, the pins are inserted through the PCB and then soldered permanently on the underside, creating a more secure but less flexible setup. That moment when builders press a fully assembled switch into a plate and hear it snap into place, click, feels simple. But that sound is the echo of an entire manufacturing chain that started weeks or months earlier. Consider what happens if any part of that chain fails. If the mold is slightly off, the housing might cause stem wobble and people complain about mushy feel. If the spring steel is inconsistent, some switches in the same batch might feel heavier or lighter. If the leaf isn't perfectly shaped, the actuation point can wander, making typing feel unpredictable. And if quality checks slack off, entire runs get known for leaf ping, overlubed stems, or factory scratch. On the flip side, when everything goes right, a switch earns a reputation. People talk about its smoothness out of the box, its satisfying tactility, its deep thock or snappy clack. All of that starts way back in material selection, mold design, and step-by-step assembly. The magic isn't accidental, it's manufactured. So the next time you slam your spacebar in a game, speed through a late-night essay, or just casually tap through your favorite sites, you're not just pressing a lump of plastic. You're engaging a mechanical device built from carefully molded housings, precision-stamped metal leaves, tuned springs, and possibly hand or machine-applied lubricant, all put together in a factory where one misaligned fraction of a millimeter could ruin the feel you've come to love. Behind every satisfying keystroke lives a story. That's how mechanical keyboard switches are made. And every time you press one, you're pressing the result of that entire invisible world.